This lab is going to try to illustrate the relationship between torques applied to an object and the corresponding rotational acceleration based on the inertia of the object. Our textbook defines torque as the product of a force and a lever arm that the force is applied to in order to make an object rotate. The lever arm is the perpendicular distance from the center of rotation of the object to the point where the force is applied. Rotational acceleration is the change in rotational velocity with time. Something like linear acceleration is the change in linear velocity with time. The inertia of a body is its resistance to its change in motion. For extended bodies like spheres and cylinders, this can be related to the object's mass and size. In this lab, we are going to choose two different objects, a solid sphere and a solid cylinder. Set their masses and radius values, apply forces, and get corresponding torques and rotational acceleration values. Done correctly, graphs of this data should give us the inertia of the object. We can compare this result to formulas of inertia that we can find in our textbook in Chapter 8. When you go to the site, use the check boxes to choose either the solid sphere or the solid cylinder. Put your choice on the data table. I'm going to choose the hollow sphere as an example of what to do. You can use the radius and mass sliders to set the initial values that you want for your object. Record these in the data table. If you slide the force slider, you will see different torque values listed. If you choose a force and hit the start button, the object will begin to rotate and you'll see a value show up for the rotational acceleration. Hit the pause button and reset button to do a new run after recording your torque and rotational acceleration values. Make sure your mass and radius values do not change when you hit the reset button. You will choose 10 different randomly picked values of the force between 10 and 50. You should spread it out over the full range just to get an idea. For each new force, write down the torque and the corresponding rotational acceleration to complete Table 1. Once you've completed Table 1, change to the other object by using its checkbox and repeat the same process. After you have both tables filled, you will create graphs from the data, one graph for each solid object. You want the torque values on the y-axis and rotational acceleration on the x-axis. You are doing this because we want to validate the expression tau equals I alpha, where tau is the torque, I is the inertia, and alpha is the rotational acceleration. Done correctly, the slope of your graph should be equal to the inertia. Make sure to extend your fitted line to the y-intercept. If you do this by hand, you will need to find the slope of the line you use to fit the data using the slope equation. If you do this using Excel, make sure the rotational acceleration is in column A and the torque is in column B. Have Excel fit a straight line to the data. Extend the line to the y-intercept and write the equation to fit the graph. The slope will be in that equation. For each object, you can use the formula for its inertia to calculate it from the mass and radius values of that object. You will then get a percent error between the slope values for that object and the inertia value for that object. The slope should be the experimental value in the percentage error calculation. What you will submit in your Word document lab write-up. In addition to answering the questions and providing completed data tables, there are two graphs that need to be properly done and appear on their own pages, filling that page. So, proper title for the graph, proper axes label, a line fit to the data, extended to the y-intercept, and if you use Excel, an equation for that fitted line on each graph. And you should have a calculations page that includes the calculation of each of the inertia values for each solid and a percent error between the slope value for that object and its inertia value.